Imagine walking through an ancient, lush landscape, vibrant with color and filled with the rich aromas of intertwined flora. At first, the beauty captivates you, but as you delve deeper into this verdant land, a subtle unease settles in. The silence is profound. The noticeable absence of birds and mammals hints at an ecosystem in distress, struggling in the aftermath of an ice age. Rising waters are on the horizon. Soon, this once thriving landscape will be submerged beneath the Pacific, some 30 meters underwater. Species that can migrate have fled in search of refuge, while those rooted to the ground face an inevitable fate. What secrets does this land hold? The history preserved in the melting polar ice offers crucial insights, for we are witnessing a similar phenomenon today. What drives the current melting of the ice caps? How will this affect the powerful climate systems governing our planet? What hidden threats lie within the ice itself? I'm Alex McColgan, and in today's episode, we will explore the significance of ice as a vital feature of our planet and envision a future where rising waters reshape our world. At Astrum, we love to investigate the vast wonders of our universe, objects whose scale and scope often elude our comprehension. Take a moment to gaze towards the constellation Cassiopeia. There lies the Andromeda Galaxy, our closest galactic neighbor at a distance of 2.5 million light-years. Despite its immense size, we find ways to connect with it. Strangely, however, looking just 80 years into our future feels like an insurmountable gap. It is essential to understand that our actions today will shape the world of tomorrow. Let's begin our journey with ice. Ice is a remarkable substance capable of storing vast amounts of energy. For context, the energy contained in modern electric vehicles, powerful enough to propel tons of metal at speeds exceeding 160 km per hour, could barely melt a fraction of the ice that could fit inside. The energy capacity of ice has been crucial in maintaining climate stability over the past 12,000 years, a period known as the Holocene. This era has been unique not only for its stable climate but also for the rise of human civilizations, made possible by the advent of agriculture. The Antarctic ice cap began to form around 37 million years ago, with the Arctic following approximately 2.7 million years ago. Both polar regions are integral to our current climate stability, their size historically influenced by Earth's position and tilt within the solar system. These astronomical movements, known as Milankovitch cycles, suggest that ice should be increasing at the poles, leading us into another ice age with falling sea levels. Yet, paradoxically, the polar ice is melting at an accelerating pace. Should all this ice disappear, we would face a staggering sea level rise of up to 70 meters, inundating coastal cities worldwide. While such extreme ice loss is unlikely, we must anticipate how much sea level rise we might expect to protect our ecosystems. To make accurate predictions, we need to understand the causes and mechanisms behind the melting ice. We recognize that greenhouse gas emissions are a significant driver of current global warming, overwhelming the natural cycles that previously dictated ice formation and melting. Surprisingly, historical data from Antarctic ice cores reveal that, in the past, rising temperatures often preceded increases in CO2 levels, a reversal of today's scenario. Both elements influence each other, but the sequence has shifted. In today's climate, thawing permafrost in the Arctic releases previously trapped carbon, further accelerating global warming. The complex interplay of CO2 and temperature fluctuations reveals the intricate climate systems at work. Greenhouse gases trap infrared radiation emitted by the Earth's surface, with the atmosphere and oceans absorbing around 90% of the energy increase. The ocean, with its massive heat capacity, plays a pivotal role in this energy transfer, allowing heat to flow from warmer areas to colder regions, primarily through ocean currents. Factors such as the albedo effect, where soot darkens ice surfaces, causing them to absorb more solar energy, also contribute to ice melt. Although improving air quality has reduced particulates in the atmosphere, which would lessen ice absorption, it paradoxically allows more sunlight to reach the surface, exacerbating the greenhouse effect. Let's examine how oceans are currently melting polar ice, particularly in vulnerable regions like the West Antarctic ice shelf. Here, we encounter different forms of ice. Seasonal sea ice doubles Antarctica's area during winter but melts through contact with the ocean. While the melting of sea ice alone contributes only a few centimeters to sea level rise, it serves as a crucial barrier protecting the ice shelves below. When this protective layer diminishes, it exposes the ice shelves to atmospheric warming, raising humidity and temperature levels. These floating ice shelves can be immense, with some, like the Ross and Ron Filchner shelves, exceeding the size of entire countries. Warm ocean currents eat away at their undersides, leading to the calving of massive icebergs that drift far from their origin. Though these floating structures contribute minimally to sea level rise, the ice they hold back is crucial. As the shelves recede, they expose glaciers and ice streams that flow more rapidly into the ocean, significantly impacting sea levels. While natural processes like snowfall and ice formation continue at the poles, they are insufficient to offset the current rate of ice loss. The additional energy in our oceans and atmosphere, captured by greenhouse gases, commits us to significant ice sheet loss. But how much will sea levels rise from the melting alone? Calculating this seems straightforward, but in reality, it's far more complicated. Earth's crust, for instance, is not entirely solid. It shifts in response to weight. As ice melts, the land beneath it rises, while coastal areas may sink, leading to localized variations in sea level. Thermal expansion of seawater has contributed to about half of the sea level rise we've already witnessed since the Industrial Revolution. This expansion can be precisely calculated, providing us with estimates for future